Hey guys, so today we're going to talk a little bit about linear data structures. By linear, I mean that they look like kind of lines, linear lines, um, as opposed to things that are kind of more graphical, maybe. So linear data structures in Python are a little bit complex, just because they feel pretty similar to one another, because basically everything here feels a lot like a Python list. So let me start from the philosophy of just abstractly. The first kind of linear data structure is the idea of a queue, which I can never spell, but I'm pretty sure is spelled this way. So a queue is like a line, right? Like at a grocery store or something, right? You kind of envision that there's some kind of a like check stand thing going on here. And we have like a first person who's in line, and then a second person who's in line, and the third person who's in line, right? And when people show up, they add to this end of the line. And when people leave, they leave from this end of the line, right? And so that's what's called first in, first out, right? Which you could really think of as this is the first come, first serve data structure. So you'll see that abbreviated FIFO. That's supposed to be an F. Whatever. Okay, so this is the idea of a queue. You might notice that you could pretty easily do this with a Python list, right? You could want to add things to the maybe left-hand side, right, the zero index, by scooting everybody down and then putting things in on the left. And then you'd want to take them off with the pop method that pulls them from the back end, right? So that's one way you could do this. You could implement this pretty quickly. It's not super hard. Another structure we might implement is kind of the opposite thought, which is like a stack of plates at a cafeteria, right? So when you put plates into this stack, they kind of look like this, right? And if I put a new plate into this stack, it just goes on top, right? So the add is here, and then the out is also off the top, right? So this is what's called a stack structure. And this is actually what a Python list already is, right? So that add and out are, and you could really think about these as happening on the script. You could think about this as the Python list, right? You just append and pop. So this is what's called the last in. Oops, that's not how you spell last. So this is last in, first out. LIFO structure. Okay, so that's kind of one option. So these are our two kind of easiest options to start with. And then there's a couple more that are harder to implement in other languages that are really super, super easy to implement in Python. And the kind of primary of those is what's called a linked list. And the Python list feels an awful lot like a linked list stuck together with an array. So an array is a statically sized list, which is a thing that we haven't run into in Python. It would be like a list that you have to tell it how many things you intend to have to start with, which, thank God, is not the way lists work. So a linked list is made out of nodes, and there's one special node called the head. Right, so that's the head node. And then each node includes some information, right? So like some piece of data. And then it also includes a link to the next node. And then that node has some piece of information and a link to the next node. And that node has a piece of information, a link to the next node. And then the last, right, so you continue on with this process. And the last node usually has a link to a none data type or something. That's kind of special to Python, right? That none data type doesn't exist in all languages, but usually it's got a null pointer or something at the end. So this is kind of the idea of a linked list. You can use a thing called a deck from the collections library to just make a linked list. It's super, super easy. The reason you might want to do something like this sort of a structure is if you have an obvious like line of succession, right? Like first we're going to try this, then we're going to try this, then we're going to try this, but you don't want to put it in a list. This is a little bit weak in Python because Python's list really is closer to a linked list anyways. So I'm kind of falling a little flat on this analogy for good reason. That said, linked lists are a really popular thing in programming interviews, so it's good to get a handle for how a linked list works. So one of your tasks is going to be to make a linked list without using a list. If you actually want to implement one in practice, you could either make one yourself, which will take you a little bit, maybe a couple hours, or you could use this collections thing from the deck library, and then you might just add things to the left and take things off from the right. That's how you'd make a queue, right? You can implement a linked list in a pretty similar way. I am going to make you implement one by hand because I think they're cool. And then the last one that I want to talk about is what's called a doubly linked list, which is the thing that you probably want to make anyways. This is also known as a Turing tape. So a Turing machine is kind of the abstract idea of a computer, and the Turing machine tape is kind of the abstract idea of RAM. This is a super cool concept. It's really, really neat. It's due to Alan Turing, who was much abused and was probably one of the more brilliant computer scientists ever. So a doubly linked list is this thing where there are nodes. Each node contains a piece of information and two pointers. One to its successor and one to its immediate predecessor. So each node points two directions, and then there's another node on each end, and each of those nodes points two ways. I guess I should redesign my arrows here quickly. And I should redesign my color scheme. So I have my blue node there has a link to its predecessor and its successor. My red node here has links to its predecessor and successor. And then I might have a green node. That green node's going to have a link to its predecessor and its successor. And you could see how this would go on in both directions. And then in the case of a Turing tape, that list goes on forever in both directions. It's bidirectionally infinite. In an implementation of a doubly linked list, in order to not suck up all the RAM, you have to end it somewhere, which is a little sad. But you can end it with a null pointer or a none type on each end. In Python, that'll be none types on each end. So I encourage you to try to implement a doubly linked list, frankly, because it's of historical interest and it's super fucking cool. So these are the abstracts of your linear data structures. And then I'm going to count on you guys to do some work to implement these things. I would suggest that you spend some time contemplating how you want to implement these first. So spend some time thinking about your file structure before you actually do any of this implementation. And then I would think about making these using a good docstring forum, get all your comments outlined, because these things will come up again in future assignments, and it'll be an awful lot easier if you can just import them. And I'm going to hope that you'll import your own. But if you find that somebody else in the class, if theirs is substantially better and you guys want to collaborate, that'll also be okay. For right now, I'd like you to kind of work on your own.